Okay, so now it's the time in the term when we start talking about nucleophilic aromatic substitution, or NAS. It is really important that you recognize that all of the rules that we talked about for EAS had obviously to do with electrophilic aromatic substitution. What you're going to notice really kind of difficult to handle thing for some students is that once we get to nucleophilic aromatic substitution, just about all the rules we learned about ortho-para-directing versus meta-directing, activating versus deactivating, all of them completely switch over because now we're looking at kind of the other side of the coin. And the way that I teach this is I'm actually going to expand the definition of nucleophilic aromatic substitution just a little bit. And so like the first thing we talk about is the true nucleophilic aromatic substitution as I learned it. And then I'm going to include two other topics that are very closely related that involve nucleophiles, but technically are not the same kind of nucleophilic aromatic substitutions per se. So let's kind of just look at the beginning list here. So I'm going to term the first one here the normal nucleophilic aromatic substitution, right? And you'll see what I mean by that in just a second. But I'm also going to include kind of this second section where we talk about what's called benzyne chemistry. And it most certainly involves a nucleophile, but is a completely different mechanistic pathway and usually is taught as like a completely separate thing. And the third type is going to be considered what I'm going to call Sandmire reactions. Now, what I'm going to define as a Sandmire reaction when we get to this third section is a little bit broader than the true picture of Sandmire reactions, and we'll talk about that. But this is really how I kind of think about nucleophilic aromatic substitution in these three separate categories. So let's jump right into it. So this very first example, I tried to use kind of the prototypical way that the ACS especially and a lot of the homework questions will kind of try to get you to recognize a particular reaction type is about to happen. Now, if you happen to see these like halogen compounds, the halogen aromatic compounds, I should say, and have these ortho and para nitro groups, that's oftentimes a clarion call that you're going to have to do some sort of nucleophilic aromatic substitution. This halogen is absolutely required. Of course, it could be a bromine, iodine, and things like that. It turns out that a normal NAS also requires at least one, often two, many times three different what we termed electron withdrawing groups before. The interesting thing is that the way that these things activate is that we need them now in an ortho and a para position in order to substitute that chlorine with whatever our really strong nucleophile is. And by the way, if you don't have a really strong nucleophile, it doesn't matter how many electron withdrawing groups you put on this thing. It just ain't gonna happen, right? So we need a really, really strong nucleophile. So I've got a mean here. Could easily be something like methoxide, like sodium methoxide, something that has, back when we were talking about SN2 chemistry, something you would consider a really strong nucleophile is going to work really well here. So the product, I'll just go straight to that, and then we'll just see a real quick mechanism. Looks incredibly simple, right? And you look at the fact that we started with a chlorine, we ended up with an aniline type aromatic compound there. And you might be tempted to think, well, that's pretty simple, right? This is just like a simple SN2-like looking thing. And honestly, most homework questions that, especially around the ACS, things that we see in homework, they're really trying to tempt you to do that really easy step that does not happen, right? It turns out that you still need to go through a tetrahedral intermediate, similar to what we saw in EAS. So let's see what that looks like. We start off by having this really strong nucleophile attack the carbon that we'd like to attack. But the first thing that happens is that double bond gets pushed up onto the carbon just to the side. And so we end up with one of many resonance forms that looks like this. And one of the reasons that I started off with this resonance form, well, first of all, that's the way my arrows kind of pushed me. But you'll also notice why it's so important to have those ortho and para nitro groups, or some sort of electron withdrawing group like a nitrile or something like that. And it has to do with the fact that there is now going to be a resonance form where we could have actually moved the double bond, or sorry, moved that lone pair of electrons here to kick that pair of electrons up. And of course, we could continue to move that lone pair of electrons around the ring and put a negative charge down here. Now, I'm going to be incredibly lazy because I know it's really nice in your book, and you're also really, really good at resonance forms at this point. So I'm not going to show you all the crazy resonance forms here, but take my word for it, they're there, and you should definitely know about them. What I'm just going to do is I am going to just go directly to the product right here. So let's just do it this way. And so I will just put it, etc., right? Plenty of resonance forms there. Now, what we're going to do at this point is keep in mind that we have to reestablish aromaticity at some point. So you can take any of these resonance forms. I'm just going to take the one that is convenient, and I'm going to show that lone pair of electrons fall back down, and in so doing, kicking off the chlorine, and now we've net substituted an aniline. And you know, I kind of chose aniline as a starting point here, really because this group right here is going to turn out to be super useful in our synthetic reactions, and it's also going to be incredibly important when we get down to those Sandmire reactions. It turns out that this thing is really, really a useful group that not only activates really strongly to ortho and para in electrophilic aromatic substitution, but we also have the ability to turn this thing into what's called the diazonium salt that you're going to see when we get to kind of part 3 of this video. And that diazonium salt itself has a ton of different note card reactions, and most of them are actually Sandmire reactions. Before we get to that though, let me show you the Benzyne mechanism and how it's different, and also some of the products are similar. But one of the things about considering this more normal NAS versus a Benzyne type mechanism that confuses students is the starting material. So make sure you recognize, right, in our normal nucleophilic aromatic substitution, it requires electron withdrawing groups, at least one in these positions, right? And we'll notice that when I do the Benzyne mechanism, those will not be there. And we'll also end up with a very rare thing when we get to this Benzyne mechanism, and that is a mixture of what kind of looks like ortho and, kind of a mixture of like ortho and meta or para and meta type substitution. So hold on. Okay, so I'm purposely trying to choose kind of similar looking starting material and actually the exact same reagent here to show you the difference between normal nucleophilic aromatic and the Benzyne mechanism. So one of the things you'll notice is that I do not have any electron withdrawing groups in any particular position on this ring. In fact, I just kind of put an R group here, right? And R is just general. I'm not saying it has to be electron withdrawing. I'm not saying it has to be electron donating. I'm just pointing out that I have something on this ring, and it's going to have some consequences for my product distribution in just a second. So this is really just me kind of like labeling a position. It doesn't actually have to be there. So notice that we've got a really strong nucleophile, but one of the things we talked about back in SN2 chemistry is that really strong nucleophiles are often really, really good bases. And of course, that's the case with something like sodium amide. It'll melt your face off. So what we're going to do is we are going to take advantage of the acid-base reactivity of this thing. I am going to show a hydrogen right here, and we're going to reach in the very first step of this mechanism and do what looks like a very odd kind of set of steps, right? What you'll notice is this crazy thing that I still barely believe that it actually exists as a reactive intermediate here. And this is called the Benzyne Intermediate, right? And in your book, it most likely probably does this stepwise, where it rips off an H and puts a negative charge right there. And then in a future step, that lone pair of electron comes down to form this thing, which, by the way, is called a Benzyne Intermediate. This is the benzyne. And by the way, when that thing comes down, then it would pop off the chlorine. But since this mechanism is just so weird, I'm not really going to bother showing it correctly. I'm just going to kind of show you how to get there. The reason that we care that there is a benzyne here is that the second step, it turns out that these two positions are as likely to be attacked, right? And the nucleophile is actually another one of the reagents that we just saw. And so what I'm going to do is I'm going to put an NH2 minus in here, right? Keep in mind there's a whole bunch of this floating around. And I am either going to take it and attack this position, or I could have taken it and attacked the other position. But when I do that, I'll just kind of choose one pathway here, and then I'll write the other product that would result. Okay, and so we can see that the introduction of that NH2 group, which is pretty much like the meta position here, and I'm going to take some of this ammonia that I formed in the first step, and I'm going to reform my reagent there, and what I end up with is one of the two products that I would observe, which puts my NH2 right there relative to my marker group. It turns out if I had done that exact same set of mechanistic arrows, but instead attacked that position, I would also end up with putting an NH2 group onto the other position. And so this is why I included that marker group, is because it's the one reaction that we're going to talk about that doesn't have kind of like a really specific preference to either orthopara or meta. This one, you always end up with some sort of weirdo mix, right? Which isn't good. It's not a great reaction, but it's something that has been asked about quite a bit in various ACS questions. So you'll notice that we don't really have a really tight control over regiochemistry in this thing. And I should mention quite often that whatever this really strong nucleophile is often paired with whatever its solvent happens to be. So like I wouldn't be surprised if the solvent here was liquid ammonia. And so that's the benzyne mechanism. I don't think of this as a very synthetically useful thing, but that is going to be made up for by the third thing that we're going to talk about. Okay, Sandmire reactions. Well, remember that amine that we talked about, or I should say aniline that we talked about as a product in the very first number, or the very first section of what we were talking about here, right? We put an amine group onto a ring, right? I don't really care what else is connected out here. It turns out that it doesn't really matter in terms of the reactivity in a Sandmire reaction. The way that we can recognize a Sandmire reaction is it almost always involves some sort of nitrite, right, with some sort of really strong acid, right? And often this thing is HCl, right? Really what we're trying to do is we're trying to get an equivalent of what's called nitrous acid, right? Nitrous acid's pretty unstable. It kind of likes to react with everything. So usually you make it in situ by treating some sort of acid and this together. By the way, that's kind of one of the reasons that people get pretty nervous about like nitrites in foods and stuff like that, because this idea is that if you happen to expose that to some sort of acid, like, ooh, maybe the acid in your stomach, right, you can actually take some amines and maybe do some pretty crazy synthetic chemistry that maybe you don't want to do in your body. I haven't actually read that research myself, so I don't know how real that is. But anyway, that's a pretty reactive species, and it turns out through a sequence of steps that's really not hard to figure out. I'll leave it for you to figure out, by the way. We end up with a compound that is really, really important, or I should say an intermediate that is very, very important. Whoops. And this is called a diazonium salt. And of course, I haven't included the anion for this thing because this is the part that we really care about. It turns out that having this, what looks like N2 is a huge driving force to put a whole bunch of different groups on there. This species itself can react in really unusual ways. If we were doing a lot of what's called qualitative analysis in lab, for instance, we'd be able to make these really brightly colored compounds. And so let's just kind of see the variety of different things that I can do with this compound. And we'll highlight the Sandmire reactions too. I forgot to label this. This is an aryl diazonium salt. So here's my aryl diazonium intermediate. Take a look at all the different reactions that I could do. The ones that were really, I think are pretty useful are things that involve copper-1 salts. So pretty much, I won't say everything, but virtually anything that you could imagine as a copper-1 salt at least has the opportunity to have whatever its anion that is paired with that copper-1 to pop onto a ring. So that's a really good way to put a nitrile on a ring. You have a whole bunch of different reactions. Let's say you wanted to put a chlorine on a ring. You could do that. And of course, we have a bunch of reactions already that allow us to put a chlorine on the ring, but maybe some of those are a little bit more difficult to do a normal electrophilic aromatic substitution. You can do kind of an oddball reaction, or I only call it oddball because there'd be no real reason to do it on such a simple looking intermediate here. But if you treat this thing with a hypophosphite, you can actually completely remove the aryl diazonium part there and just leave an H there. So in a sense, we now have the ability to pop on an NH2, use that NH2 as either an ortho or a para director, and then just have it fall off by doing some sort of protocol with this kind of Sandmire reaction protocol. That's pretty useful. That's something we're going to see when we get to synthesis quite a bit. Other interesting things that this thing can do, well, you can actually put an OH on the ring. And I think this is some sort of warm aqueous acid, I think it is. So we'll just say H3O+. Right? You can actually turn, essentially that guy used to be an amine. Now we've turned it into an OH group. Another group that, or I shouldn't say, another reaction, as I said, that's really useful is diazo dyes. So you can actually treat it with some sort of aromatic thing, right? So imagine another benzene. This thing itself can undergo electrophilic aromatic substitutions and end up with these really interesting looking diazo products where you pretty much stick whatever that aryl piece is, right? Whatever that benzene ring is, onto the benzene ring that we already had there, right? And so this is actually one of, it's probably more important in kind of a historical context. These things are all really brightly colored. It was kind of like one of the first ways that organic chemists started to figure out how to do a lot of reactions. And the reason that these guys were trying to be produced is that they had some really bright colored substances. These things are really brightly colored. And it used to be just the fact that only royalty could afford these really brightly colored clothes. Once we started to realize that we could get bright colors out of these things, it made everything a lot more affordable so that you didn't have to farm to find some really esoteric plant out in some sort of South Pacific colony. So not so important for us right there. But these reactions are super helpful. I'll probably post a resource guide that includes a couple of others. I should mention that technically a Sandmire reaction has to involve a copper-1 salt, but I think about all of these as kind of different varieties on a theme. So hopefully that helps, and we'll next time start talking about some what I call side chain reactions, and we'll probably have time to talk a little bit of like fancier coupling reactions with aromatic systems. And then we'll try to put it all together in a really nice synthetic picture.